And you were also, I was also asked that we should solve more examples. Well, these are examples. I mean, today at least, we learned the friction force, but that is the only thing new, which we spent like 20 minutes on friction force. And then we are only solving examples. These are what I will be writing on the blackboard rather than writing them on the slide. And I perfectly agree with you that this is not the most effective way of teaching. But we don't really have the material to support any other kind of lecture at now. Now, uniform circular motion in general. What we mean by uniform is that its speed is constant. Remember, velocity and speed are different things. Velocity has two properties, its magnitude, which we call the speed, and its direction. So since the speed is constant, it doesn't mean that the acceleration is zero. The direction of velocity can still change. Its magnitude is constant, but its direction can change, so it will have an acceleration. So if you look at this example, at some moment the object is at this point, at some other moment it is at this point. So the velocity vector is always perpendicular to the radial vector, because we are assuming that it is going on a perfect circle. The radius of the circle is constant. So if the radius of the circle is constant, it means that the object is not moving in the radial direction. So if I look at the object here, I can just pick up a coordinate axis. One direction is pointing radially outward, the other direction is tangential. Since the radial distance is constant, it just means that it's not moving in the radial direction. The radial direction, the component of the velocity in the radial direction should be zero. So there is only the horizontal component, which is tangential to the circle, or perpendicular to the radius at this point. Well, the direction is changing. So you see the velocity vector, initially it was pointing in this direction, now it is pointing in this direction. It basically means that the velocity vector has changed from here to there. This is the change in the velocity vector. So there's an acceleration. If there is an acceleration, which is a vector quantity, we have to determine its direction and also its magnitude. Well, the acceleration vector will be along this delta v, that we know. To determine the direction, we can just look at the angle that this delta v vector makes with the v1 vector, this angle over here. If we can determine that angle over there, then we know the direction of the acceleration. Well, if you just, that angle, well, the speed is constant. So the speed is, this is a circle in coordinate space. This is the position of my object. This is the circle of my velocity vectors. My velocity vectors just traces a circle, the radius of which is the speed of my object. This is the position, this is the velocity. So the velocity vector starts from this point and then it goes to this point. Well, the speed is constant. It just means that this is a perfect circle. The magnitudes of these two vectors are equal. If the magnitudes of these two vectors are equal, it's an equilateral triangle. So this angle alpha is nothing but 180 degrees pi minus this angle over here divided by 2. So this is this angle alpha. We will be interested in the instantaneous acceleration. If you remember, the instantaneous acceleration is the acceleration in the limit when we take delta t goes to 0. So these 2 points are taken at successive times. The separation in time between these 2 points is 0. If as delta t goes to 0, this angle goes to 0. If this angle goes to 0, then alpha just goes to pi over 2. So it is a very narrow equilateral triangle. So the base angles are 90 degrees. This just tells me that the acceleration vector, which is in the direction of this delta v, is perpendicular to the v1 vector. And it is pointing perpendicularly downward, but in this case, it is pointing perpendicularly downward which is towards the center. Or for this case, the acceleration is perpendicular to this v2 vector. It is in this direction, so it is again towards the center. Yes? Well, this is the sum of the angles inside the triangle is 180 degrees, or pi radians. That's how we define the radian unit of measuring angle. Pi corresponds to 180 degrees. So we know the direction of the acceleration. In uniform circular motion, the acceleration always points from the object towards the center. It's just like if you take a curve, your acceleration vector is towards the center of the curve, not towards the outside. And this is why we are using the radians. If you look at this circle, this delta theta in radians is defined to be the ratio of the length of this arc divided by the radius. Or the length of this arc can be written as the radius of the circle. Delta L is the radius times this angle in radians. That is the definition. Well, if this arc is the whole circle, then we say that the complete circle corresponds to a 2 pi radians. It just gives us the circumference is 2 pi r. And for this reason, we are using the radians to measure angles rather than degrees. Because if we would use the angles here, degrees instead of the radians, we would have to divide by 180, multiply by pi and all that. But when we use the radian units, we don't need to bother about all those factors. So when we want to calculate the magnitude of the acceleration, let us just denote it by A. This is the definition. The acceleration is delta V over delta T. So the magnitude of acceleration is the magnitude of delta V over delta T. Now, if you look at this diagram over here, the velocity diagram, delta V is the length of delta V is the length of this straight line over here. The length of that straight line is almost equal to the length of this arc over here. And the smaller the angle is, the more equal they become. So instead of this delta V, in this limit at least, delta T goes to 0, when delta theta also goes to 0, that is, I'm taking a narrower and narrower arc, then delta V, the length of delta V and delta S will be equal, so I just replace this delta V by delta S. But delta S, it is the length of an arc of a circle whose radius is V, and that delta S sees an angle delta theta. It is the same delta theta over there. This delta theta and this delta theta are equal. Because as my point moves from here to here, it rotates by delta theta. V1, which is perpendicular to this radius vector, V1 also rotates by delta theta. So this angle over here, V1, rotates by delta theta, and it becomes the second velocity vector. So this delta S, the length of this arc, is the velocity, or the speed, which is the radius of this circle, times this angle in radians. So this delta S is V delta theta over delta T. I should, of course, take the limit as delta T goes to 0. I'm taking two very close points on the trajectory of my object. Now, if I come back to this diagram, well, the length of this arc over here, delta L, on one hand, it is, okay, the radius of the circle times the angle that this arc sees, r times delta theta. On the other hand, I know the speed of my object is always v. It moves at constant speed for a time delta t. So the distance it covers is nothing but v times delta t. So it should also be equal to this same delta L. So because delta L is the distance it covers in time delta t with speed v. So if you just compare these two expressions, well, they are equal. So r times delta theta has to be equal to v times delta t. And you end up having delta theta over delta t. This ratio is nothing but v over r. But v is constant, r is constant, nothing depends on delta t anymore. So this limit is trivial. So the magnitude of acceleration is now v squared over r. So we know that if we have an object, a mass m, making uniform circular motion, we had already shown that the direction of acceleration is along the radial direction towards the center, and the magnitude of that acceleration is given by v squared over r. Now here we had delta theta over delta t, such a quantity, delta theta over delta t. But if you compare it with our definition of velocity, remember how we defined velocity was the difference in the position divided by the time it takes to make such a change in the position. That is how we define the velocity. Now delta theta is the change in the angle. So my object moves from this point to this point, changing the angle, its angle relative to the center by delta theta in a time delta t. So this is what we call the angular velocity or angular speed. It is the speed, but of the angle. It is the rate of change of the angle. And we had just shown here that the angular velocity is nothing but v over r. Well, you can object. Velocity, we defined it as a vector, not as a scalar quantity. At least in more than one dimension. In one dimension, velocity was a number, a positive number or a negative number. In this case, it's also, you can imagine that delta theta can be both a positive or a negative number only. So in that sense, it is still the velocity. Okay, the same things. These things we have proven, we had obtained that the angular velocity, the acceleration is perpendicular to the velocity, and the acceleration is given by v squared over r by just using some geometrical means. But we can do the same thing by using some vector algebra and some calculus. You should be getting used to warming up with vector algebra and calculus. Eventually. Not right now, but eventually you should. So if we would use vector calculus, how we would prove the same things? Well, this will be the position vector of the mass. It shows where my object is relative to the center of the circle. Well, the distance, the length of this vector r is nothing but capital R. And from the definition of the scalar product, we know that r squared is nothing but the scalar product of r with itself. This is the definition. Well, the scalar product would have the product of the magnitudes times cosine of the angle between them, but the magnitudes of these vectors is nothing but the radius of the circle. The angle between them is 0. If I differentiate this r squared with respect to time, as my object moves, I want to see how this r squared changes with time. Well, it doesn't change. The circle has a constant radius, and I know that my object is moving at a constant distance from the origin. It is 0. At the same time, if I take the derivative of this thing, remember the radius vector is the r vector is the position of my object. Since my object is moving around, r vector is changing. It is magnitude is not changing. If I take the derivative, it is just the derivative of the product of two functions. It is r dot dr by dt plus dr by dt times r. Well, the scalar product, I can just change the order. It doesn't make any change. The derivative of the radius vector with respect to time is what we defined as the velocity. So this already proves me that scalar product of the position vector of my object relative to the center of the circle with the velocity vector is 0. But if you remember again the definition of the scalar product, this just proves that the velocity vector is perpendicular to the radius vector. So we already know that the velocity has to be perpendicular to the radius vector. Well, what else we know? We know that the speed is constant. Well, the speed is the magnitude of the velocity vector. So the speed squared we can write as the scalar product of the velocity vector with itself. Then we do the same trick. We just take the derivative of both sides. We know that the speed is constant, so derivative of v squared of this thing is 0. But on the other side, the derivative of this quantity is twice the velocity times acceleration. So this also has to be 0. So this proves that the acceleration vector is perpendicular to the velocity vector. Acceleration. We know that the velocity is perpendicular to the radius vector. Acceleration is perpendicular to the velocity vector. Now, what about its magnitude? Well, this is the explicit form of the radius vector. It is cosine theta in some x direction, sine theta in the y direction. Theta is the angle it makes with the horizontal axis. Now, this vector over here has unit length. It is a vector which we call r hat. It is the unit vector in the direction of the position of my object. And its length is r. Since the object is moving on a circle, we know that the length of the position object has to be r. This is unit length, so this is the position of my object. The velocity, well, the velocity is the time derivative with respect to t. If I just take the time derivative of this expression with respect to time, remember x hat and y hat vectors, they do not change in time. They are just constant vectors which I picked up at the beginning. But this r hat vector is changing in time, because as my object moves, the unit vector pointing towards my object, it should also change its direction. So if you just take the derivative of cosine is just minus sine, derivative of sine is cosine. Well, theta, the only thing that depends on time here is theta. So if I'm taking derivative with respect to t, it is derivative with respect to theta, and then the derivative of time with respect to theta. So this is what I have for the velocity. Well, this is again a unit vector, which I define to be the theta hat vector. It is the direction in which the theta is increasing, whereas the radius is constant. Remember, when we call the x hat vector, x hat direction is the direction in which the x component is increasing, whereas the y component is constant. Just like that one here, theta hat is the direction in which theta is increasing, but r is constant. R hat is the direction in which r is increasing, but theta is constant. Now, we are given, by telling us that we are studying uniform circular motion, we already know that the radius, the velocity, the speed is constant. The speed is just this quantity over here. This has unit length, so it is the magnitude of this thing, r d theta by dt, which we can denote by, which we have always been denoting by v. We know that this is constant. This is the theta by dt is what we call the angular velocity, and that is also constant. Now we have the velocity. This is the constant speed of my object. So now I can just take the derivative once more to calculate the acceleration. The derivative of sine is cosine. The derivative of cosine is minus sine. Again, theta is the only thing that depends on time. So I first differentiate with respect to theta, and then differentiate theta with respect to t. So this is my acceleration vector. Well, d theta by dt, it is just omega, the angular velocity, which we had already derived here, that it is v over r. This is the derivation. Since this is constant v, d theta by dt is v over r. So this is v omega. If you just take this minus sign out, what remains is this vector over here, the r hat vector. So we have proven that the acceleration vector is in the direction of the radius vector, in the opposite direction. It is pointing towards the center, and its magnitude is given by v omega. V omega is v over r, so it is v squared over r. So here we didn't make any use of geometry. But there are two different ways we had derived the same quantity, the acceleration. They should and they do give the same result. I'm sure currently the previous derivation seems to be simpler to you, but I'm hoping that at the end of this year, this derivation would seem much more simpler to you. Any questions? Okay, if this just sounds so puzzling to you for the moment, you can forget about it. There will be a homework question related with this one anyway, so you will work on it during the homework. You can just remember the first one. The important lessons from here. If we have uniform circular motion, the acceleration is pointing toward the center. And the magnitude is v squared over r. Those are the things that are important results of these derivations. Now, since we have an acceleration, there is an acceleration, then Newton tells us that there should be a force, and the direction is, since the acceleration points towards the center, the force also has to be pointing towards the center. And the magnitude of this force has to be equal to mv squared over r, and it should be directed towards the center. So the question is, what causes this force? What is the origin of this force? Unless there is some other object which provides this force to our mass will not be able to do circular motion. There has to be some means of creating this force. Well, it will not be so uniform. Well, for example, if you just take this pouch and if you rotate it, what is the source of this force in this case? Any ideas? My hand. Well, my hand is not touching the pouch. It's the string, basically, yeah. String, due to my hand, my hand applies a tension on the string, and then the string just carries that tension to this pouch, and the pouch feels the force towards the center, not outside, towards the center. And that force causes my pouch, that force prevents my pouch to go straight, but it just rotates. So it just pulls it inside so that the pouch cannot go away. Now, if at any instant, now let's do it horizontally. I'm just rotating my pouch. Sorry. At any instant, I just release the force, it just goes straight. It doesn't curve anymore. In this example, I had my pouch rotating. At this instant, I released it. The only force was a vertical gravitational force. So as it went down, there was no horizontal forces. At this moment, the velocity vector was pointing in this direction. So after I released it, the velocity vector always pointed in that direction because there was no, it went accelerated downwards, but the horizontal component was constant. It was always pointing in that direction because there were no force to change the horizontal component of the velocity. So when I release it here, it doesn't just continue making a curve. Because there's no force, it will not change its velocity. It will go straight. Well, this is an example of a so-called a conical pendulum. Well, conical pendulum, we can study next Thursday. Questions? If you want to study these slides are already on the web page. So, I have this pouch. I'm just rotating it. It is making a circular motion. Let's assume there is uniform. At this instant, let me open this diagram. Just imagine that this mass is my pouch, and this is the horizontal plane, and my pouch is rotating. At this instant, the velocity of my pouch is pointing in this direction. It is perpendicular to the acceleration, the radius vector. If I release it at this moment, now there's no more any horizontal force acting on my pouch. If there's no more any horizontal force, it means there is no horizontal acceleration of my pouch. If there is no horizontal acceleration, the horizontal component of the velocity will be constant after this point. Since the horizontal component, the moment I released the pouch, the horizontal component was pointing in this direction, it will continue moving in the same direction with constant speed. Of course, there is a vertical acceleration, so it will go down. But in the horizontal direction, it will be making a motion with constant velocity. Now, the moment I release it, suppose I released it here, it will not continue to make a curve and move there. The moment I released it, if it has this velocity, it will continue in this direction. It will not bend because there is no force for it to bend anymore. So if I release this mass at this instant, it will keep moving in this direction. If I release it at this moment, it will keep moving in this direction. This, since it's rotating, it will not just continue rotating and getting further. It will not follow such a trajectory. Follow the laser light. It will not go like this. It will go straight. Other questions? Yes, the speed will be constant. It will go with the same velocity infinitely. Because if there is no force, there is no change in velocity. It is not just in the theory, by the way. Or it's not just in the lectures that the velocity is constant if there is no force. Also, when you go outside, whatever you observe there, they follow the same rules. If you think that what you observe outside is following some different rules, then you are thinking in a wrong way. Come to the class, ask that question, and we will discuss what is wrong. So how many of you still think that when the car takes a left turn, you will feel a force towards the right? Okay, there is one. Well, I'm sure there are more than one of you. If you are moving in a car, the car makes a left turn. Do you feel a force towards the right? You don't even feel that force. There's no force to feel. The only force you feel is the car pushing you towards the right. So you are pushing the car towards the left. Sorry, you are making a left turn, so the car is pushing you towards the left. That is the force you feel. You are pushing the car towards the right. Okay, so you two, just lean on towards each other. Both of you. Push each other. No, lean it towards each other, not just with your hands, shoulder to shoulder. Okay, so you are going towards this direction, right? But the force you feel is towards the other direction. So the same story in the car. The car is pushing, if the car is turning in this direction, the car is pushing you in this direction. But you are pushing the car towards the other direction. In these dynamics, what causes you to accelerate is the force that you feel. The force that you act on something else will be creating an acceleration on that something else, not on you. Then on Thursday, we will have a Blackboard lecture.